Okay, so in this video, we're going to continue talking about the concept of the conservation of mechanical energy, and we're just going to be finishing up some examples with mechanical energy conservation. And so just to kind of recap, mechanical energy is defined as the kinetic energy of an object plus its potential energies. And we've talked about two types of potential energy before, spring potential energy and gravitational potential energy. And usually, in most situations, an object only has one type of potential energy, although it doesn't have to be that way. You could have both spring potential energy and gravitational potential energy at the same time. Now, the idea of conservation of mechanical energy is that you have some quantity, in this case mechanical energy, that is conserved, meaning that that is a fixed number that doesn't change. Okay, and so let's see how this applies in different situations. Okay, so here we have a cart at the top of a hill, and I'm going to give this a label. Normally I would call it point A, but there's already a point A and a point B over here. So I'm going to call this point C. Just to give it a name, it doesn't really matter what you call it. Um, but we're going to start off with the cart starting from rest at the top of the hill, and we're going to call that point C. And the cart has a mass of 400 kilograms, and the top of the first hill is 90 meters tall. Okay, now the first question says calculate the mechanical energy at the top of the hill. Okay, that is, calculate the mechanical energy at point C. Okay, so the mechanical energy at point C, I'm going to write E mech C. By definition, would be equal to the kinetic energy at C plus the potential energy at C. Now, there's spring potential energy and there's gravitational potential energy, but in this case, there's nothing in the problem having to do with the spring. And so I'm going to infer from context that the only other type of potential energy we have is gravitational potential energy. Okay, so I have the kinetic energy at point C plus the gravitational potential energy at C, for which I'm going to write EGC. Okay, and the first question is basically asking me to find this value. Now, I can expand this out because I know the equations for both of these quantities. Kinetic energy is 1/2 mv squared. Okay, so the kinetic energy at C would be 1/2 times m times vc squared. Okay, where m is the mass and vc is the speed of the cart at point C, at the top of the 90-meter hill. Plus Eg is mgh, and so I would write this mghc, where again here HC means the height of the cart at point C. Okay, and I actually know these values because I know that the cart starts from rest at the top of the hill. And so that means VC is 0. In other words, the kinetic energy at point C is 0. And so I would have 0 plus mghc, and I have 400 times 10 times the height at point C, which is 90. Okay, and so E mech C, I would just type that into the calculator. I would do 400 times 10 times 90, and that would give me 360,000 joules. Okay, and that's the mechanical energy that the cart has at the top of the hill. Now notice again, I didn't have to call it point C. I could have called it anything I wanted to, but that's the answer to the first question. Okay, so I found the mechanical energy at point C. Now here is the concept of mechanical energy conservation. This is how much mechanical energy the cart starts with. Mechanical energy is conserved as long as there's no resistive forces. And there's nothing in the problem to suggest any resistive forces like friction or air resistance. In other words, I've met the condition for mechanical energy being conserved, and so this 360,000 joules that I have at the top of the first hill, I have the same amount of mechanical energy the entire time. So even as the cart goes down, reaches point A, and then goes up again, that whole time, right, I have 360,000 joules of mechanical energy. Okay, and so the overall mechanical energy doesn't change. In other words, the way I would write that is I would say E mech C is equal to E mech A, which is equal to E mech B. Okay, so the mechanical energy is the same at all of those points. Now, what does change is how the energy is split up because you have kinetic energy and potential energy. And so you can have one of those go up while the other one goes down. Okay, so for the second question, we're asked to calculate the mechanical energy at position A. Um, and so what is the mechanical energy at position A? Well, the mechanical energy at position A, of course, like we just said, is the same as the mechanical energy at position C because it's conserved. So that's 360,000 joules. Now, in the last question, it says calculate the speed of the car at position A. So we know that E mech C is equal to E mech A, and we know that's 360,000 joules. We also know that E mech A, by definition, would be the kinetic energy at A plus the potential energy at A. Okay, so I have EKA plus EGA, and I can expand that out, right? I can do 360,000 is equal to 1 half MVA squared plus MGHA, except that if you look at the picture at point A, the height is 0 because it's on the ground. We can assume the reference point is on the ground. Okay, so that means HA is 0. That means that second term actually goes away. And so we have 360,000 equals 1 half times 400 times VA squared. And so you can rearrange this and find VA by itself. Okay, so see if you can get that. So 360,000 divided by 200, take the square root, you should get 42.4 meters per second. And that is the answer to example 2. Okay, and so this is just a very basic conservation of mechanical energy problem. Now, I do want to point something out, by the way, that this calculation we just did does not depend on the shape of the hill. Okay, which is one of the benefits of doing energy calculations rather than calculations with force or with Newton's laws. Because if we did this as a force problem, it would be much more complicated to figure out because you've got the force of gravity and you've got the normal force, but the normal force like changes all the time. And plus, as it goes down the hill, um, it's almost like going down an incline, and so you know that you've got components of the force of gravity going down the incline that are changing all the time. With energy calculation, we don't have to worry about any of that. Okay, and so this gives us a way to solve problems. And again, the answer would be the same regardless of the shape of the hill, provided that there is no friction, okay, which there's not in this problem. Okay, so pause there if you need to look at that some more. Okay, so let's do a few more examples with conservation of mechanical energy. Okay, so example 3. It says a compressed spring is used to push a 5 kilogram block along a floor. The spring has a spring constant of 500 newtons per meter and is originally compressed by 5 centimeters. As the spring decompresses, the block gains kinetic energy. Calculate the kinetic energy and speed of the block when the spring has decompressed to 2 centimeters. Okay, so let's say we have a spring. Okay, so let's say here's a spring. And let's say this is the spring's equilibrium position. And the spring is pushed in to here. Okay, and so let's say that this separation is 5 centimeters. So originally the spring is compressed by 5 centimeters. That's what it says in the problem. Okay, and so I'm going to say this is position A. Now we're asked to find the kinetic energy and speed of the block when the spring has decompressed to 2 centimeters. So in other words, the spring is pulled back to here, and then when it's let go, it starts to move back to equilibrium. And so point B is going to say be let's say right here, where this separation is 2 centimeters. Okay, and so we're asked to find the kinetic energy and speed of the block when the spring is decompressed to 2 centimeters. All right, so let's see. I know that there's nothing in here about resistive forces, and so mechanical energy is most likely conserved. And so I know that E mech A is equal to E mech B. Okay, so let's talk about what type of energy I have here. So mechanical energy is kinetic energy plus potential energy. All right, so I can expand this out. I can say EKA plus, now based off of the context of the problem, there's nothing having to do with height, and so the potential energy in this situation is going to be spring potential energy. Okay, and so that would be ES A, the spring potential energy at A, and that's equal to EKB plus ESB. All right, so let's see. I have the mass, I have the spring constant, which is K, and I know that it's originally compressed by 5 centimeters, which means that XA, remember X is the displacement from equilibrium in a spring, is going to be 0.05 meters. Okay, don't forget to convert centimeters to meters. I also know that we want the kinetic energy and speed of the block when the spring has decompressed to 2 centimeters. So this is going to be XB. So when I go to expand out this equation, I have 1/2 mVA squared plus 1/2 KXA squared is equal to, I'm actually going to leave this here right now because we're actually asked to find the kinetic energy um, at B. And so I'm just going to leave that as EKB for right now. And then ESB would be 1/2 KXB squared. Okay, so if I want to know what is the kinetic energy at point B, all I have to do is plug in some numbers and solve. Now, you can infer from context that the spring is pushed in and then it's let go from rest. Okay, and so that means VA is going to be 0 if it starts off from rest, which means that whole first term is going to be gone. Okay, and so if I go over here to start plugging in values, I have 1/2 times 500 times 0.05 squared is equal to EKB plus 1/2 times 500 times 0.02 squared. And now I just need to subtract and get EKB by itself. Make sure you don't forget to square the displacement from equilibrium though. Okay, so I've got 0.5 times 500 times 0.05 squared. And then I'm going to subtract 0.5 times 200 times 0.02 squared. And that gives me EKB is equal to 0.21 joules. I'm just going to make sure that that's correct. 0.02 squared times 0.5 times 200. Okay, so there you go. So that is the kinetic energy of the block when the spring is decompressed to 2 centimeters. Now, of course, what's going to happen is you're going to pull the block back and you're going to let go, and eventually the spring is going to go back to equilibrium and the block is going to fly off. Okay, and so if you've ever played with like Nerf guns, this is basically the principle behind a Nerf gun where you like pull the thing back, you're basically like cocking the spring, and then you can pull the trigger and it like shoots a little dart at people. That's basically the idea behind that. Okay, so we found the kinetic energy when the spring is decompressed. Now if we want to find the speed, all we have to do is use the kinetic energy equation, which is 1/2 mv squared. And so I know that 0.21 is equal to 1/2 times 5 times VB squared. And now I just need to rearrange and solve for VB. Okay, so I've got 0.21. I'm going to multiply both sides by 2, divide both sides by 5, and then take the square root. Okay, and I get 0.29 meters per second. Okay, so there you go. That is example 3. Pause it there if you need to look at that some more. Okay, so here is example 4. So example 4 says a toy cannon uses a small spring to launch a 5-gram marble up a ramp. The spring in the cannon has a spring constant of 50 newtons per meter and is pulled back 3 centimeters before being released and shooting the marble out from rest. Now, the first question says, does conservation of mechanical energy apply? Check notes. Okay, so remember, mechanical energy is conserved in any situation where you don't have any resistive forces. Okay, so do we have any resistive forces in this situation? Well, it doesn't say anything about friction in the problem, And later on, it says assuming the ramp is frictionless. And so we can probably infer from context that yes, mechanical energy conservation does in fact apply. Okay, so there's two questions here. I want you to try to answer the first question on your own. Calculate the speed of the marble right after it leaves the cannon. And just to give you a hint, the marble is going to leave the cannon when the spring reaches its equilibrium position. Okay, so it's originally pulled back 3 centimeters before being released. The marble is going to leave the spring or leave the cannon once the spring gets back to its equilibrium position. Okay, so using that as a hint, try to see if you can answer the second question here using mechanical energy conservation. Calculate the speed of the marble right after it leaves the cannon. Okay, so in this situation, we basically have three different positions. We have point A, which is when it's been pulled back 3 centimeters. We have equilibrium position for the spring, which I'm going to call point B, and then it's going to slide and eventually reach the top of this ramp, which I'm going to call point C. Now, because mechanical energy is conserved, I know that Emech A is equal to Emech B is equal to Emech C because mechanical energy is conserved. Okay, so let's start with Emech A. All right, so I expand out Emech A. What type of energies do I have at point A? Well, mechanical energy is kinetic energy plus potential energy. All right, so Emech A, the kinetic energy would be 1/2 mVA squared plus the potential energy, but based off of the picture, if it's on the ground, and let's say that's the reference point, there's no gravitational potential energy, there's only spring potential energy. Okay, and so that's going to be 1/2 times k x a squared. Okay, so that all of that is mechanical energy at A when the spring has been pulled back 3 centimeters. Now point B is when it's going to leave the cannon, that is when the spring is back at equilibrium. Okay, so I'm going to write 1/2 mvb squared plus 1/2 kxb squared. But xb is going to be 0 because at this point it's going to be back at equilibrium and it's going to leave the toy cannon. Now, what about at C? Okay, well at C, the mechanical energy at C would be 1/2 mv squared. So that's 1/2 mvc squared plus the potential energy at C, but there's no more spring involved now. Now, based off the context of the problem, the only type of potential energy I have is gravitational potential energy. By the way, I don't want you to think that you always have to have some type of potential energy, because that's not the case. I mean, it's just that one depends on a spring and one depends on height above the reference point, and you don't have to have either one. It just so happens in all these problems that we only have one or the other. Okay, and so here I'm going to write mghc to represent the gravitational potential energy at C. Okay, now I can use what I have to answer the first question, calculate the speed of the marble right after it leaves the cannon. So in other words, I want to know what is VB. And I know some values. I know the mass is 5 grams, which needs to be converted to kilograms. So that's 0.005 kilograms. I also know the K for the spring is 50 newtons per meter, and that's initially pulled back 3 centimeters before being released. Okay, so I can start plugging some values in. Okay, so I have 1/2 times 0.05 VA squared. Okay, well, it's pulled back and released from rest, and so that tells me that VA is 0, so 0 squared, plus 1/2 times 50 times 0.03 squared. That's the displacement from equilibrium, and that's equal to 1/2 times the mass times VB squared, which is what I'm looking for, plus 1/2 times 50 times the displacement from equilibrium at B, which is 0, because I already established that that's when it's going to leave the cannon, when the displacement is 0 again. Okay, so actually that term goes away and that term goes away. And so now I can very easily rearrange this equation and get VB by itself. Okay, so the answer you should have gotten for VB, I'm just going to go to my calculator and plug some values in really quickly. All right, so the answer that you should have gotten, just going to take the square root, is approximately 0.95 meters per second. So that's the answer to the second question. Now the last question says, assuming the ramp is frictionless, calculate how high up the ramp the marble travels. Okay, so here we're looking for the height at point C. All right, so see if you can do that last part of example 4 on your own. Okay, so to get the height at point C, basically it's the exact same process, except instead of doing, the mechanical energy at B, you do the mechanical energy at C. And so I would have 1/2 times 50 times 0.03 squared is equal to 1/2 mvc squared plus mghc. But look, it's going to go up the ramp and eventually it's going to stop. And so if we want to know how high up the ramp travels, at some point it's going to stop, and that's the height that we care about. But if it stops, that means the kinetic energy is going to be 0. And so if this is 0, that whole term goes away, and all we have to do is find hc. Okay, and so it's a simple matter of plugging values in to get hc by itself. Okay, so I'm just going to do that now. I'm going to do 0.5 times 50 times 0.03 squared, and then I'm going to divide by the mass, which is 0.005, divide by 10, and I get hc is equal to 0.45 meters. Okay, and that's the answer you should have gotten for the last part of example 4. Okay, so pause there if you need to look at that some more. Okay, and then the very last thing I want to talk about, this is the very last part of the unit, is a certain type of problem that you're going to see on worksheet number 3, the conservation of energy, or conservation of mechanical energy worksheet number 3. And these are situations where you actually do have resistive forces like friction or air resistance. And you might say, but wait, I thought mechanical energy is only conserved if there are no resistive forces. Okay, and that's true. But we can still answer questions using mechanical energy conservation as long as we correctly account for the loss of energy. And so I'm only going to do one example of this type, but it's important that you understand the approach to these problems. Okay, so here's the key concept. Any mechanical energy that is not conserved must be lost due to work being done by a resistive force. Okay, any mechanical energy that is not conserved must have been lost due to work being done by a resistive force. Remember the concept of work. This is one of the first things we talked about. The concept of work is energy added or removed by a force from an object. Okay, and so if we have a situation where we lose mechanical energy, where it's not conserved, that loss must be accounted for by negative work being done by a resistive force. Okay, and so the last couple of problems you have in worksheet number 3 involve work being done by a resistive force. And it's really important that you understand when I talk about work being done by a resistive force in this context, you're not using the work equation to do this calculation. This is a concept question. This is you understand the concept of work as the transfer of energy to or from an object. Okay, and it's really important that you understand this because otherwise, when you go to answer this type of question, you're going to be trying to use a work equation and it's not going to work because you don't have enough information. Okay, so when I'm asking to find a work in this context, I'm not talking about using the work equation. I'm talking about this is a concept question where you have to understand what work actually means. Okay, so this is the last example in this unit. Let's see what this looks like. Okay, so example 5. So it says a spring containing 6 joules of energy, of course, that spring potential energy, is used to push a small 0.2 kilogram box along a rough surface. When the box has traveled 4 meters, it is traveling at a speed of 6.75 meters per second. Okay, and so let's talk about this. So originally we have 6 joules of energy in a spring. So let's say we have a situation where there's a spring, and let's say the equilibrium position is here. I'm going to call that point A. Or sorry, the equilibrium position, I'll call it point B. And let's say it's compressed back some amount. I don't know how far. It doesn't matter. Okay, but at some point it has 6 joules of spring potential energy, and the spring is going to push a box. Let's say here's the box, and then what's going to happen is the box is going to slide across the ground. So let's say the box ends up over here after the box has traveled 4 meters. Okay, so let's say this is 4 meters. Now I'm going to call this point C. Okay, so let's take a look at this. First of all, you would ask yourself, is this a situation where I can use mechanical energy conservation? And your first instinct should be no, because it tells you it slides across a rough surface, which means you have friction, which means mechanical energy is not conserved. Okay, but let's see by how much it's not conserved. So Emec A would be the kinetic energy at A, which is 0 because it's the spring is acting on the box and the box isn't moving yet. Okay, so that's EKA, which is going to be 0, plus the potential energy at A, which we're actually given in the problem is 6 joules. Okay, so that means the mechanical energy at point A is just 6 joules. Now, what about the mechanical energy at C after it's slid 4 meters? Okay, well, that would be, 1/2 mvc squared. There's no more spring over here and there's no height, so the only type of mechanical energy it has is kinetic energy. Okay, so 1/2 times 0.2 times 6.75 squared. Now, if you put that into your calculator, 6.75 squared times 0.2 times 0.5, you get 4.55 joules. Okay, so that means at A, it has 6 joules of mechanical energy. At point C, it has 4.55 joules of mechanical energy. Very obviously, mechanical energy is not conserved. Now we get to this question. Calculate the work done by friction. You're not using the work equation in this problem. Okay, this is a concept question. Think of it this way. We start with 6 joules of energy. We now have 4.55 joules of energy. Where did the energy go? Okay, well, that means that we must have lost energy due to work being done by friction. How much energy did we lose? Well, let's see. We ended up with 4.55 joules. We started with 6 joules. All right, so that means that we lost 1.45 joules of energy. So how much work did friction do? Well, it did negative 1.45 joules of work. How do I know that? Because work is the transfer of energy to or from an object, and I know that's how much energy was transferred out of the object. Okay, so again, we're approaching this as a concept question, not using the equation for work. Okay, so make sure you understand that. Now, the last question, we are using the equation for work because now it says estimate the magnitude of the frictional force acting on the box. Now that I know the work done by friction, I know that friction would be going in the opposite direction of motion. And so the work done by friction would be equal to the force of friction times the displacement times cosine of 180 degrees. And so if it's moving to the right, then the force of friction would be acting to the left. So if I want to know the magnitude of the frictional force, I would just plug in 1.45 is equal to FF times the displacement, which is 4, times cosine 180, which is negative 1. Of course, cosine of 180 degrees is negative 1. And so to get the force of friction, all I have to do is divide both sides by 4, and I'm basically done. And so if you do that, you get FF equals 0.36 newtons, and we're done with the question. And so that is example 5. And so this is not exactly a mechanical energy conservation problem, but it's a situation where if we understand the limitations of mechanical energy conservation, we can still use it to solve problems as long as we take into account the energy missing, knowing that that energy that's missing, the reason it's missing is because some type of resistive force like air resistance or drag or friction must have done negative work and removed energy from the system. Okay, so that is example 5, and that is the last example that we have in this unit. All right, so as always, please let me know if you have any questions, and I'll see you guys in the next video.